Thanks.
Thank you.
Thank you. Hi, everyone. Welcome to the second lecture. The lecture series is called Sharp Restriction Theory. And yesterday, we mostly focused on introductory philosophy and spherical sharp restriction. Today, we'll mostly be focusing on parabolas and cones. They have interpretations in terms of PDE, strict rights inequalities for both the wave equation, and that's going to be the topic for today. Okay, I'll mostly be using the board. I will show you one picture towards the end, so at that point we'll set up for you. All right. So the same way as we started with the sharp Hausdorff-Young inequality yesterday, today we'll start with the sharp Harvey-Influence solid. That's going to be the first topic. So Harvey-Influence. This is also very classic. Also very classical inequality in harmonic analysis, but we report with the loop. So this guy, we have two functions, f and g. They both have Rd as the domain, so we're integrating over R2d. We're defining by this x minus y in absolute value to the lambda, integrating the x and y, and we hope to bound this by the product of the LP norms of f and g. Okay. F, we need to do the LP of Rd, and G, we want to do the same LP of Rd. This is not necessarily the case, and in principle, you could put F in LP and G in LQ, but for the sharp version, I'm going to tell you about, we need them both to be in the same space. So in this way, you reduce matters to quadratic form. And so there's an optimal constant. I'm calling it L, that depends on lambda, the parameter lambda, and the dimension B. And I'm calling it L because this was on my lead. Okay, it's one of the lead's famous theorems, and I need equal to D. All right, so what does it tell us? Well, first of all, the inequality has assumptions. This inequality is a box, and I'm calling H like this. And so for the inequality to hold, we need open any dimension. We need the parameter lambda to be between 0 and D. And since we're forcing both f and g to be in the same LP space, scaling dictates that p is given as a function of p and lambda by 3b over 2b minus 3. Okay. And so if you are not concerned about the sharp constant, you can prove this in many different ways. You can make this break up into two pieces, a small ball and the complement of the ball, and use holder in one region with the LP bounds of the maximal function, the Harvey-Influence maximal function in the other region, but that's not going to give you the sharp constant. So the sharp constant is actually given by a beautiful expression. We write it for you. It's lambda over 2 gamma function over 2. You divide it by gamma b minus 1 over 2. It's different. And then gamma over 2 divided by gamma b. Everything raised to power lambda b minus 2. Okay. This is what Lee proved, and he proved this by exhibiting one maximizer, which in this case is what we call the conformal factor. A function 1 plus x squared raised to negative. Okay. He proved that this function maximizes HLS. He wants to know that this is a global maximizer for this function. You just plug it in, you can compute both left hand side and right hand side, and can prove that this is the best function.
Diogo, okay. Is it clear that the constant lambda L does not depend on P?
Yes, just because P is given in terms of P and lambda.
Okay.
This is because I'm forcing,
yeah.
I'm forcing both to live in the same LP. It's a very good question, open question as far as I know, to compute the optimal constant when P is equal to Q. And that's not wrong. But the diagonal case is wrong. Leaf's proof is very clever. I'm not going to describe it. Instead, I just want to say a few words about an alternative proof that came about 10 years later in the early 90s by Carlin and Voss. And that is called the method of competing symmetries. Okay, so competing symmetries means the following. This is Carlin not just for the HLS inequality, I think he also got the Sobolev inequality, and from there it became like a popular method to sharpen the number of inequalities. So we basically identify two symmetries of the inequality. And symmetries means either something that keeps both the left-hand side and right-hand side in pairing, or something that has a monotonic effect on one of the sides and keeps the other one. Okay, so the first symmetry here is rearrangement in the sense of Riesz rearrangement, like we were discussing yesterday. So Riesz rearrangement does not change the LP norms. And the Riesz rearrangement inequality, if you consider three functions, f, g, and this function here, with the denominator, implies that the left-hand side will not decrease if you replace f and g by their rearranged versions. Okay, that's one symmetry. The other one, I think that's the striking observation of Lee, is a conformal invariance of the inequality. What does this mean? The inequality is over RE. So if you have RE, you can take a stereographic projection and lift it up to the sphere. And once you're on the sphere, you can rotate the sphere and then project back by an inverse stereographic projection to RE. If you do that, you don't change the left-hand side of the inequality, and the right-hand side also stays the same. So in some sense, it's a sequence of symmetries where first you rearrange, then you use the stereographic projection to rotate on the sphere, come back, rearrange again, and so forth. We'll make these are the two competing symmetries, and this will create a maximizing sequence that converges strongly to the constant function of the sphere. The constant function of the sphere maps back via the inverse stereographic projection into this function too. And that's why it's a maximizing. Okay, so I'm saying this to illustrate 2 points. First of all, when you have like a hard problem in analysis, sharpening inequality, and that you know in non-sharp form, usually the proof involves revealing some deep facts about the inequality. In this case, the conformal invariance is not needed to prove the non-sharp form, but it plays a crucial role in all the known proofs in the sharp form. The second point is that sometimes symmetries, they sort of talk to each other, they conspire with each other to produce the only possible candidate to maximize. That's what happens here, and that's what's going to happen later on in some sharp restriction inequalities article. Okay? All right, so that's the motivation. Let's jump right into sharp restriction and let's talk a bit about symmetries. Okay, and I want to discuss this in two contexts, so I'm going to split the board. On the left, we're going to talk about the Schrödinger equation. On the right, we're going to talk about the wave equation. Okay, and let's see where this leads us. So the Schrödinger equation, this is ut equals I of what's u, and some initial data. So u is a function of both time and space. When time is 0, I just take some initial data x naught. Okay. So this is a dispersion, the PDE, in the sense that different frequencies propagate at different speeds. And one way to solve it is to take the Fourier transform. So here I denote tilde the space-time Fourier transform. I'm taking Fourier transform both in time and space. And we can check easily with Fourier variables tau and c. These are dual to t and x. So this is one-dimensional, this is d-dimensional. This is just delta of tau minus c squared and x. What does this mean? This means that there's an associated manifold to this equation, which is given by tau equals c squared. That's the equation of a parabola in R equals 1. Okay. So this is associated to tau c in R 1 minus d. Again, I'm emphasizing the fact that tau is in R, c is in d, such that tau is c squared. Okay, so this is the full parabola in R equals 1, so it's non-compact. So in principle, that could be an issue for the Stein-Thomas argument from yesterday. Remember, I said you can replace a sphere by compact hypersurfaces of non-vanishing Gaussian curvature. This is non-compact, but to our help comes the fact that this is also a homogeneous surface, so it has some scaling, and the scaling makes, remember, any point Stein-Thomas was essentially scaling variant at small scale. So that's what we use here to check that the Stein-Thomas type argument applies to the full parameter, not just the piece. Okay, and the curvature is this, right? Parabola has everywhere positive Gaussian curvature. Okay, so once we have this formula, we can take we can do full inversion. And so U X is showing it on the bigger. And Y X, which is given by an epsilon, where you got Tx, we have C squared C. Again, the Fourier transform is on the right. F times C, and your integral U over R. Which is 4. Okay, so from this representation, immediately we have L2 mass conservation, right? So for every T, if you just look at the L2 norm of this guy is that it does not L3, in particular to its value at T equals 0. So this is called mass conservation. But remember, the equation is dispersive. So even though the mass is preserved, it spreads with time. And this spreading in time is what lies at the heart of Strickland's proof. It's very influential Strickland, who was very much aware of Stein-Thomas method and adapted the proof to conclude that even if the problem is not compact with an unbounded surface, you still have a similar estimate there. And so what Strickland's proved for the Schrodinger propagator was, okay, if you replace this 2 by 2 plus 4 over d, so you're slightly above 2, you can still bound that uniformly in terms of the output of the initial rate. So this is 2 plus 4 over d, e. Sorry, 1 plus c. This is space time, and this is bounded by a dimensional constant. He did not care about the precise value of the constant. Okay. And so this is the Strickland's estimate for the Schrodinger equation. Yes. Any questions? This is a quick crash course on Schrodinger. Let's do a similar one for the wave equation. So the wave equation is second order in time, so it's u t equals Laplace u. So we need two initial conditions, u and t. X0, I'm just going f and g. I will want f to be homogeneous over which 1/2, and g homogeneous over the minus 1/2. Functions in RD. So contrary to the Schrodinger equation, the wave equation is not dispersive, it's partly dispersive, partially dispersive, which means that different frequencies, they may propagate at the same velocity, but the direction of propagation is determined by the frequency. We can do the same trick, so we can do space-time Fourier transform for the solution of the wave equation, and what we get is now a delta. Absolute value of theta minus absolute value of c times various Fourier transforms of initial data, proper normalization to get a hat plus the sine theta divided by 2 times absolute value of c times g hat of c. Okay. And again, you see that there's an associated manifold to the wave equation, which is given by mod tau equals mod c, which defines the equation of a two-sheeted cone in R1 plus c. So the associated manifold is tau c in R1 plus c, where absolute value of tau equals absolute value of c. This is a real number, this is a vector, this defines a two-sheeted cone. And the two-sheeted cone, again, is non-compact, homogeneous, but this time the Gaussian curvature vanishes identically. Okay, right. So non-compact, homogeneous, but the Gaussian curvature is identical. That in principle could be a problem, but what comes to the rescue is the fact that, well, Gaussian curvature is a product of all principal curvatures, so it's enough for one of them to be zero for the product to be zero. That's exactly what happens. Precisely one principal curvature is zero, all others are non-zero. And so street arcs are in the place. Okay, so I'm going to write that. All but one principal curvatures are non-zero curvature is what we need for restriction technique. Okay, so in the same paper, Sweetheart did not do just paraboloids. It actually considered generic quadratic surfaces, so both paraboloids and cones are examples. Very notation. So the solution of the wave equation. So the wave propagator, just call it S. Okay. It depends on initial wave F and G. And at the point dx, this is just given by cosine E squared root minus Lavashi plus sine D squared root minus Lavashi minus Lavashi J plus. So the same paper proves that this wave propagator is bound on LP, not for the same value of P, but for a different value. It's twice B plus 1 over D minus 1 R 1 plus B is bounded by a dimensional constant times the H1/2 norm of the pair FG. Okay, so this is Strickler's estimate for the wave equation, W. And let me just mention that this space here, curly H, are the findings. So for a generic S, the square of the HS norm of this pair is, by definition, will be valid in terms of the Fourier transform. So there's F at base to the power 2 times C to the 2S, there's a C to the C minus 1, G at the C. Okay. So when S is 1/2, you have the H 1/2 norm of F and the H minus 1/2 norm of G. So they are in the right space with respect to what I defined. Okay, so let's talk a bit about these exponents. So we have 2d plus 1 over b minus 1 and 2 plus 4 over b. So we've seen one of these exponents yesterday, and that was this guy, right? This was the Einstein-Thomas exponent for the sphere. If you check, this is exactly the same exponent in one dimension higher. Okay, so they are both Stein-Thomas endpoint exponents. It's just that this one corresponds to RB, this one corresponds to R1 plus D. D and 1 plus D are precisely the number of non-vanishing principal curvatures of the cone and the parabola. Okay. All right. So the title of this section is symmetries, but I still didn't talk about symmetries. So what symmetries are there? By symmetries, I mean symmetries of the PDE, right? So operations that perform on the function U, so that both if U is a solution, then U composed with that symmetry is also a solution. So you have some pretty easy ones to verify, like space-time translations. Dilations. Dilations will be either parabolic dilations in the case of the Schrödinger equation or quadratic / isotropic dilations in the case of the wave equation. You have scaling. You have space rotations. And you have phase shifts. Okay? In some sense, these are the expected symmetries that are verified both for Schrödinger and for wave. Okay, so we'll just say all of these are okay for Schrödinger and for wave. Of course, we have to be a bit careful, and dilations are different We're talking about parabolic dilations for the Schrodinger and isotropic dilations for the. But then comes some special symmetries that are not so obvious and make the whole theory rich. And I'm talking about Galilean transformations. Galilean transformations, which are a symmetry of the Schrodinger equation, but not of the wave equation, and Lorentz boosts. Okay, so Lorentz boosts are a symmetry of the wave equation, but they are not a symmetry of the Schrodinger equation. Okay. And there are some other hidden symmetries like the pseudo-conformal transformation for the Schrodinger equation. We won't need those. These are the symmetries that are going to be important for us. And so we give this symmetry group a name. We say that all these five guys with parabolic dilations plus the Galilean transformation forms the Galilean group symmetries. That's the group of symmetries of the Schrodinger equation. And these five guys with the isotropic dilations plus Lorentz boosts, they form the Pontachet group, which is the group symmetry group for the wave equation. Okay. Any questions so far? Okay, so let's make this sharp. Still haven't talked about sharp streetcars. So let's do it now. Section 3 is maximizers. Let's start with left-hand side. So let's do maximizers for Schrodinger. Maximizers for Schrodinger. So that's the PDE perspective. The streetcars for Schrodinger corresponds to restriction on the parabolics. So we can talk about parabolic for maximizers for parabolics. As this is closer to what we were doing yesterday. Yesterday was maximizers for spheres, so now we're replacing spheres with parabolics. Okay, so the question is, we have a nice inequality. Here it is, the streetcars inequality for the Schrodinger equation. We want to understand its sharp features. So new maximizers exist. If they do, what are they? Can we characterize them? What's the optimal cost and so on. Okay, so first of all, good news, maximizers exist in all dimensions. Okay. This seems easy, but it's actually an important open problem in the case of the sphere. Yesterday, I told you about the two sphere and this pre-compactness result of crystal shell. Okay, something similar happens for the circle, but in higher dimensions, it's not known. Maximizers probably exist, but nobody knows how to do it. Okay, for Schrodinger, they exist in all dimensions. They exist. Okay, this is for all one. And it follows by a result. Profile decomposition, if you want, for the Schrodinger equation, of the blue patterns from 2006. Okay, so the question here is not really about pre-compactness of maximizing sequences and the existence of maximizers. That has all been done. The interesting question is about the shape of the maximizers. Right? So what's known? Gaussians are known to sometimes maximize certain instances of the streetcars inequality for the Schrodinger equation. And actually, there are instances that are a bit more general than the equation S on that board, just because they involve mixed norms on the left-hand side. So I'm going to write them down. Same L R in T, L Q in space, 1 is E. And usually it's still on L2. So I'm rewriting it in the following just because I want to have this flexibility of measuring the T norm and the X norm in different exponents. Of course, if R equals Q, then they will necessarily have to be equal to 2 plus 4 over D, and we reduce to this equation, not in general. Sorry, the options maximize this equality in the following 3 cases. So E, Q, R are allowed to be 1, 6, 6, 1, 4, 8, and 2, 4. Okay. So dimension is either 1 or 2. The first and the last case correspond to actually Q equals R, so that's not mixed norm, it's this case. When D is 1, we have 2 plus 4 over 1, that's 6. And the last case is D equals 2 non-mixed norm, so 2 plus 4 over 2, that's 2 plus 2, that's 4. Okay, so this is an L2L4 inequality, and this is an L2L6 inequality. Now there's this interesting new case where Q is not the same as R. Q is well, both are even integers, one divides the other, but they're different. Okay, and so who prove this? This is actually a collection of results. The first paper that I'm aware of, still not 20th century, is by Ozawa and Tsutsumi from 1998, in which they did not explicitly exhibit maximizer, they computed the best constant of this inequality. The sharp streakers inequality on the two-dimensional parabola or Schrodinger equation, one plus 2 dimensions. Okay, so they just do that case, and just the sharp constant and not even say anything about maximizers. Okay, then the two pure norm cases were built by Foskey in 2007 James paper. And the mixed norm case, this 148, was first observed by Oliveira in 2000. Some alternative proofs of these facts have been given. So there's a nice paper by Kuldamak Czerniński in 2006, where they do they sort of find some new beautiful representation formulas for the Strickland's integrals, and they cover again both pure norm cases, but differently from Foskey. Then there's a famous EVCH paper. So this is Bennett, Carver, and Hundertmark from 2009, in which they show that heat flow methods are useful for these problems, at least when the exponents involved are even integers. And so they recover all three cases with a quadratic heat flow, where they show that quantities have the relevant monotonicity properties, sorry. And then more recently, Lisbon in 2019 gave an alternative proof of all three cases using classical properties of orthogonal elements. Okay. So I would like to, I guess, draw a parallel to what we did yesterday. We spent some time with an L2 for inequality. Let's spend some time with an L3 for inequality now on the problem. Okay, so let's do that for the case study. I'm thinking how to organize the results. So case study. Let's do L2 of 1. Non-spatial dimensions. And this is an extension inequality on the parabolic. Okay. So extension on the parabolic should correspond to streakers for sure. I'm taking the extension point of view just so that the parallel with yesterday's lecture is more clear. Okay, so the two-dimensional parabolic we already defined it. Subset of A with tau equals C squared. And equipping the paraboloid with projection measures. Projection. This is what I'm calling mu. Okay, so mu at a point of tau C is just delta of tau minus C squared B power x. Okay. So if you want this exclamation mark, you just take the function f on the parabola. F mu is a measure supported over the parabola, and we take its Fourier transform. Right? There's an L4 to L2, sorry, L2 to L4 estimate for this extension operator, and that's what we are going to try to estimate and put in chart. And if we learn anything from yesterday's discussion of the sphere case, was that if you want to understand F sigma convolved with F sigma, maybe you should start with the simplest case where F is the constant function. Okay, so let's see what we can say about the convolution of a projection measure on the parabola with. Okay. So this is a function on R3, and it should live in the say the support of this measure should coincide with the sum of the parabola or the parabola with itself. Right? And this sum, if you want, is you can take it extended an enlarged parabola, and everything that lives inside is going to be in support of this measure. But that's going to come out of the computation anyways. Okay, so what is this? This is an integral over R2 plus 2. It depends on both C and tau. And what do I need? I need to, so geometrically what's happening is that I'm taking 2 points on the parabola, and I want those 2 points to sum to tau on C. Tau on C is not necessarily on the parabola. It's on the support of this measure, which is the sum of the parabola itself. Okay, so I take 2 points, let's say eta squared, and zeta squared. I'm going to try to make my zetas sufficiently different from x's. If there's any confusion, just let me know. And I get rid of this delta function. Right? So this delta function encapsulates all choices of points eta squared and zeta squared from the parabola. Whose sum equals the point of tau x. And then I integrate in the end. Okay. Turns out that this can be computed, and I'm showing you a somewhat different computation from the convolution computation from yesterday. Yesterday, remember, we tried to do the same thing for the sphere, and we just paired it with an arbitrary radial function, and we use the definition of the convolution with mean and so forth. Here, I think it's easier to do it directly. And why is that? Well, the point is that now we have two arguments on the delta function, and we are both codifying the fact that we have two equations. Right? First guy equals 0, and the second guy equals 0. Well, if the first guy equals 0, then zeta is necessarily equal to c minus zeta. So we can use this to reduce it to one argument on the delta. So this is delta of the tau minus eta squared that we changed, but now we use the first equation to set up zeta is just c minus zeta. And instead of an integral over R4, we have an integral over R2. Okay. Now this expression is a bit unbalanced. I would like to make it more balanced. And by unbalanced, I mean okay, that eta here and c minus eta here. You can just do a change of variables, a translation, and if you replace tau, sorry, eta by c over 2 plus eta tilde, then these two squares will simplify because we'll get something like a plus b squared and a minus b squared. So I suggest this in the variance because with the translation, we are integrating over R2, so that's okay. And this whole thing becomes delta of tau minus c squared over 2 minus 2 eta squared. That's what I mean by a more balanced expression. Also because remember, we're expecting something that depends on tau and c, and the variable integration eta now appears just once. Okay, twice. That made the computation a bit difficult. Now it appears once. And this is an integral that we can actually compute in polar coordinates in R2. Okay, so let's do that. This is a radial function, so the angle doesn't really matter if I have a factor of 2 pi. And then integral from 0 to infinity, delta of tau minus c squared over 2 minus 2r squared. By the polar coordinates, I think I have factor of r with that. And the d theta was already integrated out. Okay. Let's change variables once again. One last time actually. So 2r squared and call it s. Which means, okay, so 4r equals ds. So I can multiply 4 here, divide by 4 there. 2 pi over 4 is 6 pi over 2. And what I have is the delta into tau minus 6 squared over 2 minus s ds from 0 to 2. Okay. And I guess we're done because this integral will be either 1 or 0, depending on whether tau is or is not greater than or equal to c squared over 2. Okay. So I'll write this as 5 over 2 times the indicator function of the region tau greater than c squared over 2. So geometrically, what's happening? I think that's also part of the interest. So we start with a parabola, tau equals c squared. So this is the tau axis. It's a one-dimensional variable. This is the c plane. It's a two-dimensional plane, but I'm just presenting you with a slice of the picture. And what we're seeing is that the convolution is supported on the interior of this enlarged parabola. So this parabola is tau equals c squared over 2. And what you obtain when you sum the parabola itself is everything that lies inside this region. Okay. So if you're inside this region, if tau is greater than c squared over 2, the convolution projection measure is constant, equal to pi over 2. Pi over 2 just helps you in normalization, and outside is 0. Okay. So I'm sort of making a dramatic pause here because that's the main point of the argument. So the key to getting a sharp streetwise inequality is to realize that the measure, convolution measure, mu convolving mu, is constant inside itself. Constant. Inside. Inside. Okay. Notice that I'm not saying anything about the boundary, about the values of the boundary. They will not matter for us today because the boundary has Lebesgue measure 0. We're going to integrate this, and when integrating, these null sets can be disregarded. That's not going to be the case on the talk on Thursday. Okay, so on Thursday I'll talk about discrete analogs of this thing where the boundary matters because it has positive measure. Here it doesn't. So that's a difficulty that does not show. Okay. All right, so let's see how we use this observation. Then 4, this is 5. Let's do 6. Okay, so we said something about mu convolving mu. Now we have to say something about f mu convolving f mu. So what happens at a point p tau, c? Well, for the lack of any better idea, we can use Cauchy-Schwarz. And Cauchy-Schwarz tells us that this is how mu convolving mu times x squared mu convolving x squared. So the pointwise inequality that holds for every tau and c, and it's a consequence of Cauchy-Schwarz, the same way as we use Cauchy-Schwarz with an appropriate positive measure. The measure, of course, involves the delta. In this case, it's the projection measure. It's a positive measure, and so there's no secret here. So this is just Cauchy-Schwarz. Pointwise. Okay, but if you have it pointwise for every tau x, you can integrate both sides in tau x. With tau x, x is R1, x2, and do the same thing here. Integrate in tau x, R1 plus 1. Okay, but now what have we learned in the previous world? Well, we know that this guy is constant inside its support. So I can, if I want, take out the L infinity norm of this guy. But the L infinity norm is actually a common value to all the points in the support. So a sort of a trivial application folder, and this guy we can put it equal to pi over 2 on its support. So a sort of a trivial application folder tells me that this is at most pi over 2. This comes out of the interval, and then you rearrange what's left inside. And you conclude that that's the autonomic. The formula. Okay. So we started with the left-hand side of the Striger's inequality for the Schrodinger equation. Right? That was Schrodinger propagated in L4. So that's F mu hat in L4. We rewrite using Poincaré as the L2 norm, F mu converted to F mu squared. And we have an estimate. That's sharp. If we can make both inequalities, Cauchy-Schwarz and Holder, equalities at the same time. Good news, we can. That happens precisely when F is a Gaussian. Okay. I'm going to write it. Both inequalities are equalities if a certain functional equation is satisfied. I'm going to write it. So this is satisfied almost everywhere. And by solving this functional equation, which is tricky, I'm not saying that this is easy, it requires some ingenuity, you can prove that F is a Gaussian. Right? My main point today is not to illustrate the solution of a specific functional equation, so I want to, well, just not to. I forgot to say, but I can say it here, that once you have the example of a maximizer, for instance, it's standard Gaussian e to the minus x squared, then you take its property, you let the Galilean group of symmetries act on this propagator. So remember, Galilean group was all these expected symmetries plus Galilean transformations. Okay, so you let the Galilean group act on this, and you get all the answers. Okay. So I just showed you why the standard Gaussian is a global maximizer. To get all of them, you just let the Schrodinger propagator act on the standard Gaussian, pick your favorite composition of symmetries from the Galilean group, you'll get another maximizer, and this list exhausts all maximizers. Okay. Since we're talking about symmetries, let me give you an alternative way to think about this computation here. This computation might seem a bit mysterious. Why is it constant? Is there a conceptual reason why it's constant? There is, actually. And the reason is related to symmetries. Maybe I can make it explain here with a different. So imagine that we have any point on the support of the two-fold convolution. Let's call it C. We want to show that the value of the convolution does not depend on the location of the point. So it will be enough if we can check that all these points have the same value as one distinguished point, for instance, that is 0 on over. And this is when C is 0 and tau is 1. How can we do that? We can do that by performing a sequence of symmetries. Namely, if I am already on the tau axis, I can bring a generic point, let's say tau, 0, tau star. I can bring it down to 0, 1 via a parabolic dilation. So the question is, how do I move a generic point to the tau axis? You do it with a Galilean transformation. Okay, so there's a Galilean transformation that takes a c tau to 0, tau star. In that case, tau star is given by tau minus c squared over 2, which is convenient because this is positive or non-negative, precisely where when you're in the interior of the support, because the boundary condition says tau equals c squared over 2, so tau is greater than c squared over 2 if you're in the yellow region. In which case, the Galilean transformation moves you from here to here, at which point you just parabolically dilute to 0, 1. Okay? So the convolution is indeed constant inside its support, also for symmetry reasons, at which point you just have to compute it at 1. Okay? All right, so I'm almost done with the discussion of Schrödinger. Let me just mention Lieb's conjecture. Implicitly, in his 1990 Williams paper on Gaussian kernels and only Gaussian maximizers. And this is that whatever I'm describing here, that Gaussians maximize the low-dimensional cases of streetcars, that should hold in all dimensions. Okay? So Gaussians should maximize inequality S for any B related. Okay? So this is known in dimensions 1 and 2 and open in higher dimensions. And I would like to mention one last result by Chris and Kilogram from 2014, who basically tell us to not get too excited. Okay? What does that mean? So Gaussians have a real chance of being global maximizers for streetcars in all dimensions, whenever we have a pure norm on the left. But streetcars are just one particular, they're like Stein dots, right? They're just a P equals 2 case of restriction inequalities. Restriction conjecture for the sphere, or restriction conjecture for paraboloids in general, is much more general. We should be talking about an LP to LQ extension inequality. What Christian Kilogram showed is that Gaussians only have a chance of maximizing such inequalities, general LP to LQ, if and only if P is 2. Okay? So when P is not 2, Gaussians are not even critical points of the associated Lagrange equation. So they have no chance of being global maximizers. Let me write it. So Gaussians are critical points for LP, LQ extension on the parabolic PB in R1 plus V, if and only if P is. Okay. But of course, the extension conjecture, the restriction conjecture for the parabola predicts a vast range of exponents P and Q, most of them are not equal to 2, for which this inequality holds, and for those, maximizers may still exist, but Gaussians will not lose their job. Okay? I'm emphasizing this because now I want to start talking about the wave equation, and there are equivalents of Lieb's conjecture and Chris Kilogram, but more recent ones. Okay, let me tell you the proof. So this is a very nice observation. The proof is not super difficult. It uses complex analysis and heavily relies on the fact that Gaussians are entire functions. So you can perform a number of complex miracles to make this work. Any questions?
Yes.
Yes.
Is there any information when P is not 2?
Any information?
Yeah.
I mean, from their paper, the only thing is that Gaussians fail to satisfy the Lagrange equation.
But in the positive sense, nothing is known.
Nothing is known. It's known that maximizers exist conditionally on progress of the restriction system. And that's a recent paper that exists. So I guess maximizers exist, but they are not what you would naively expect if you think this Gaussian stuff propagates all over. It doesn't. It's very specific of P equals 2. Any more questions? Okay, so I guess it's time to relax. I'll erase the boards and then we talk about wave. You're relaxed. Now we can go to section 4, maximizers for the wave equation, which of course means home extension. Okay. So I didn't erase that part on purpose because we have the wave equation, the fact that it's a cable manifold is a home, the wave propagator, and the streetcar inequality, pure norm streetcar inequality for the wave propagator. So H1/2 to LP, where P is endpoints time twice. Okay, so I call it W, that's inequality W. What do we know about sharp features of W? What about maximizers? Well, first of all, just like in the paraboloid, they exist. Okay, they exist in all dimensions. Maximizers exist. Now, the relevant dimensions are equal to 2. In D equals 1, it's just the union of two lines, and lines don't have curvature. Nothing is crystal there, but D equals 2 or higher. So existence of maximizers is a result of Hanush from 2012. It's part of his creation thesis. So again, the question is, what do maximizers look like? And much less is more. So there's only one instance in which inequality W has been sharpened, and that's when D is 3. In that case, this function 1 plus x squared raised to 1 minus 3 over 2 and then 0. Remember that we need two initial conditions for the wave equation. This is a maximizer. Maximize inequality W over there if E equals 3. Okay, so if D equals 3, 1 minus E over 2 is minus 1, so this is just 1 over 1 plus x squared, sort of a bubble. And the exponent is 4. It's twice 4 over 2. So that's an L2 plus 4 inequality. That's maximized by this type. In which case, we can ask what are, okay, this is one maximizer, what are all maximizers? Well, we play the same game. We let the wave propagator act on F are 0. This is my initial data. I let the concatenate group. Okay, group. From this way propagator, remember, concatenate group just means all 5 expected symmetries plus Lorentz boosts. Lorentz transformations in general. And I'm saying Lorentz boosts because you can get a general Lorentz transformation by composing Lorentz space relation. So they're all there. And you get all mass answers. Okay. This is again the result of in the same paper, passed in 2007. Dealt with this lower dimension Strickers inequalities for both Schrodinger and wave. And what's happening is pretty similar. So what's going on is Strickers inequality is on L2, L4 extension inequality on the cone. We call it gamma 3. So gamma 3 is a 3-dimensional cone as well. So this is the 2 cone. We have 2 sheets on the cone. If you want, this is like C plane, C here, and the power axis. And maybe to better explain what's going on, let me consider the upper sheet of the 2 sheet cone. Let me call it gamma 3 plus. So this is just the part corresponding to power equals plus absolute level of C. I'm choosing one of the 2 signs. So this guy I call it 2 cone. This guy I call the 1 cone. It's just abbreviation for 2 sheeted cone and 1 sheeted cone. This guy comes with a measure. It's not the projection measure anymore. It's, if you want, the Lorentz invariant measure. It's the natural measure for this problem, which I'm calling mu plus. And the difference with projection measure is that you have to divide by input values. Okay, this is related to the effect of Lorentz transformations have, for instance, on the left hand side of inequality. Okay, so this is a Lorentz invariant measure. And what happens, just like with the parabola, is that the convolution, the 2-fold convolution of this Lorentz invariant measure is constant inside the circle. Constant inside its circle. Again, boundary values don't matter because the boundary has the Lebesgue measure 0. And what's the support? Well, the support now I'm just talking about the 1 cone, the other sheet of the cone. You have to add the cone with itself. And what happens when you do that is that you don't enlarge the cone, you cannot leave the cone, but you get every point on the interior of the cone. Okay, so this region here, the yellow. This region is the support of the 2-fold convolution. And that convolution is constant there. And again, you could do some delta calculus integrals, you don't need to. Symmetries are enough. We have to compare orange. We need to compare the value of an arbitrary point in the yellow region to, let's say, the point 0.1. And we do that similarly by first applying a Lorentz boost. Lorentz boosts have these hyperboloids as invariant manifolds. So you will Lorentz boost to go here. So this is from a generic C now. We go to 0 tau star. Now tau star is just C minus tau minus C. Minus C. And then you do a conic dilation or an isotropic dilation to bring you back to the point 0.1. Right? So no computations are needed, you just have to check this invariance of the symmetries of the wave equation properly into invariances of the convolution measures. Okay. Right, so once you have that, the exact same proof that I had applies, and you get a sharp inequality. Sharp inequality W, and you can check where equality goes if F hat is of the form exponential minus C divided by C. In the case of Schrödinger, I didn't really make a distinction between f and f hat because we can conclude that f was a Gaussian and the Fourier transform of a Gaussian is a Gaussian. That's not the case here. If f hat is this guy, you have to compute its Fourier transform, which can, and this is the conformal. So this function here. Sorry, 1 minus c over 2. And then over 1 minus and this is so you get 1 over 1 minus x squared, and that's where this side comes from. Okay, it appears because it's the Fourier transform of an exponential divided by c, which is the solution to the functional equations that show up when you do the exact same proof as before. Okay, let me tell you that this works. So this was the d equals 3 case. The d equals 2 case also has an even exponent, which is 6. So you could try to analyze a threefold convolution. And the proof works in d equals 2 for the threefold convolution if you just consider the one column, the one shifted column. But the proof fails for the two shifted column. So there's a subtle difference between one shifted column and two shifted column. Two shifted column is in general higher, corresponds to the full wave equation. One shifted column is still interesting from the PDE point of view. It corresponds to the so-called half-wave equation. Alright, so I think this work more completely. The same way as Lee made a conjecture for general dimensions, Foskey made a general conjecture for general dimension. In his paper, in the same paper, we do this, which is that this is a general shape of mass. 0 maximizes wave for any in any dimension where the problem exists. Okay. So what's the status of Foskey's conjecture? So here's the key. Foskey's conjecture makes sense both for the 2 cone and for the 1 cone. So let me present it. 1 cone and 2 cone. Again, the 2 cone corresponds to W as it is over there. The 1 cone would correspond to the field half W, which is the streetwise inequality for the half-wave equation. Okay, so if D is 2, Foskey's conjecture is okay for the 1 cone. That's what I just said. And D equals 3. Foskey's conjecture is okay both for the 1 cone and the 2 cone. I sort of sketched the proof of the D equals 3 case of the 2 cone, and I told you the same thing applies for the 1 cone in lower dimensions. Okay, so this yes is all part of Foskey's theory. And I guess the reason behind his conjecture, the reason why he was led to this conjecture. Now, a few surprises happened, not just in dimensions 2 and 3, but in higher dimensions. I'm going to split higher dimensions in even or you'll see one in just a second. And the surprise came in the PhD thesis of Giuseppe Negro, who disproved Foskey's conjecture in even dimensions. Okay, so we know this Negro. I guess I'm keeping my convention of just telling you publication dates, but this showed up on archive in 2018. Okay, so it's been more. Okay, so Foskey's conjecture fails in even dimensions. What about the other cases? We don't know, but there are local replacements for it. So locally, in a vicinity of these functions, and what you obtain from it by applying the wave propagator and letting the concave loop act on them, that there are local versions, and these local versions were proved by Philippe Gonçalves and Negro. It showed up in 2022, but this work followed that. Okay. So the situation for the 2 cone is more complicated, and whenever we have nodes, we don't get. I mean, what was proved was actually something very strong, that these candidates to be maximizers, they're not even critical ones. Right? So they fail to satisfy our Lagrange. Because of that, they cannot be local maximizers. Since they're not local maximizers, they cannot be local maximizers. That's what happened. So we don't really have good candidates here, and that's why I suggest that we focus on the one from Institute. Okay, for the remaining period. By the way, how much time do I have?
15 minutes.
15? That's okay. All right, good. Thanks. Okay, so I told you that once we have a maximizer, we have all maximizers by the symmetries actually, but in this case, we would like to have a concrete realization, concrete expression for the set of all maximizers. So, and that's easier to do in Fourier space. Okay, so if you take a set of maximizers, in the B equals 3 case, right? This here. So it's not so easy to describe what happens to this function when you let, for instance, a generic Lorentz boost composing the phase shift and a scalar. It's easier on the Fourier side. And so on the Fourier side, so if you look at the Fourier transform, you say maximizers, what you will think is 1 over c times exponential of a big C plus b log c plus c. Okay? Here, B is a complex vector with real part less than minus the real part with A, so that these guys have good integrability properties, creating the right circular space, and C is a general vector in C. Okay, so this is the set, the complete set of maximizers when B is 3. And since we have Gaussians for the Schrodinger equation, I'll take the liberty to call these guys Foscans. Okay, so this guy is a set of Foscans, and in the same way as Gaussians play a role in crystal kilograms result, I'm going to tell you an analog for Foscans. Of course, I lost one. Of course, so we say. All right, so what if P is not 2? The same way as we have here the crystal kilogram result that tells us don't get too excited. The obvious maximizers only have a chance of really maximizing the inequality if P is 2. Can we have an analog, conic analog here? And as I said, let's focus on the one cone because the situation for the 2 cones is more complicated. We don't even have an obvious candidate to be a maximizer. The natural guy fails even to be a. Okay, so let's work with the one cone. So let's define the extension operator in the one cone. It's given by this zero integral. F is a function we find on the web, and we should predict the Lorentz invariant measures. Okay. So the restriction conjecture on the cone, on the one cone, predicts that there is an LP to LQ restriction inequality. So you start with an LP function on the one cone. LP with respect to this Lorentz invariant measure, XC over XC. And the extension operator is modeled from LP to LQ. If and only if, this is of course a question mark because that's the contour of the restriction conjecture, which is open in higher dimensions. P is between 1 and 2B over Q minus 1. And Q, by scaling there, has to be only 1Q. And that's because the cone is around, that's P plus 1 over B minus 1 and 2. Okay. So this conjecture is known in low dimensions. Contrary to the sphere and the parabola, which is only known in the plane, the conic restriction conjecture is known in the three lowest dimensions. Okay, so when B is 2, this is classical, and you do parabola, and you do 84. We just use these orthogonality methods that are similar. It's like a conic adaptation of the proof of the restriction conjecture in the not a big surprise. But big surprises came later. B equals 3, this is a big paper of Wolf, from Wolf, 2001. He uses some fancy bilinear machinery to establish the conic restriction conjecture. And more recently, perhaps even more impressive, is the case B equals 4, which is due to Wu and Hong Wang, appeared in 2022. And this is an adaptation of polynomial partition to give a full proof of the restriction conjecture on the Cohen dimension. Okay. In higher dimensions. All right, and so here's our theorem. This is the theorem with Giuseppe Negro, Betsy Silva, and James Dalkes. We put it on our last year. And the title of the paper is titled that I decided to give to today's lecture. I also don't remember exactly what it is, something along the lines exponentials rarely maximize Fourier restriction curves. And this is, if you want, the conic equivalent or the Chris kilogram result that we were talking about. Okay, so our theorem has two parts. Firstly, so there's an inequality here. This is the essentially inequality for the one cone. C. So maximizing sequences. For C. Think on that. Modular symmetries. So in particular, maximizers exist. This is of course conditional on progress towards the restriction conjecture. Like if we prove that for all exponents being Q satisfied, this will prove the restriction conjecture. It's not the case. If we know the restriction conjecture for some values P and Q, in an open range below that, we get the precompactness of maximizing sequences and therefore existence of maximizers. So maximizers exist, but they're not what you would naively expect from the previous discussion. So Fosskians are critical points. If and only means okay. Maximizers exist, but Fosskians don't have a chance to be global maximizers unless pleased. Okay, and this part is harder than Chris kilogram because we cannot rely on any complex analysis. So I told you that their proof was partly based on the fact that Gaussians are entire functions. You can do all sorts of magic with them. Our Fosskians on the Fourier side, they are singular converged. Like there's this one of the C-singular that just messes up the analysis. Okay, so this proof, just like Negro and Gonçalves-Negro's results that I talked about before, is based on a tool called the Penrose transform. And I would like to show you some pictures of the Penrose transform. So maybe Adam, if you could help me with that. So in the few minutes I have left, I would like to just tell you briefly about the proof of this theorem. The proof involves basically 3 steps. We can cover. So 3 steps. The first step is sort of comparing extension of the cone with streetcars for the half-wave equation. Second step is the Penrose transform and the effect it has on the Penrose equation. And the third step is the analysis of this fundamental integration. So at some point, the Penrose picture will be. Okay. Then I can talk about step one. Okay, so this is only about step two, so we have time for step one. Step one, I told you, we need to connect the extension to the one cone, extension problem to the one cone with triggers for the half-wave equation. So what does that mean? We can define a half-wave propagator e to the ITD g of x, and that's just this side. And then there's the transform. And importantly, we are not considering the measure dxc over mod c. That was a Lorentz invariant measure for extension of the cone. Here, there's a dictionary that translates between half-wave, the triggers for half-wave and extension for one cone. And the dictionary is G hat C should be F of mod C, C B of mod C. Okay, so this is the relevant guide for the half-wave propagator. F is a function of the cone. And if you could relate G hat and F via this formula, you see that there's no need to divide by mod C here. Okay. So if we do this, what happens is that the half-wave propagator for G equals the extension, the conic extension that I defined in the previous form for F. Okay. All right. Step two involves the Penrose transform. There it is. Before talking about the Penrose transform, I should talk about the Penrose map. So the Penrose map is what I'm trying to depict in this picture. This is a conformal compactification of spacetime. Fancy words, right? Spacetime equals R1 plus D. And what we are doing is, okay, a point in R1 plus D, and we write it as T comma X, and X, you write it as R times omega. So the X in RD, you write it in polar coordinates, R times omega. R is just a number, positive number, and omega is a point on the sphere. And so the Penrose map takes T R omega, and it changes both R and T, but it doesn't change omega. Okay, omega stays, and so it's actually just acting on two variables. So the variables little t and little r are mapped into big T and big R according to this formula here, involving the sum and differences of arctangents. Of course, the arctangent is there because that's a compactified, and we check. If you take R1 plus C and go by this map, you get this sometimes called the Penrose diamond, which is this triangle, where, for instance, a line T equals constant is mapped into this curve. Okay. All right, so that's the Penrose map. And this sort of lifts to a transform that takes functions defined on R1 plus D to functions defined on the C. And I don't have much time to go into the details, but the important thing about this Penrose transform, not the map, the transform that takes functions to functions, is what effect does it have on the simplest function on the sphere, or conversely, on our candidate maximizer. Our candidate maximizer, it's this function. We know it's maximizer when D equals 3. This is mapped via the Penrose transform, which takes functions on RD and maps it to functions on ST on the sphere, to the constant function on the sphere. Right? And this is not too much of a surprise because this map is conformal. And this is a conformal factor. So it's sort of a Jacobian that shows up when you change variables according to the conformal transformation. Since it's the Jacobian, nothing is that, just have the constant function equal to 1. All right, so I would like to show you what happens at the level of the Euler energy equation, but I'm not sure if I have time. Is my time?
But you can continue a bit.
But the time is up, right?
Yeah, time is up.
Time is
You can continue.
Okay, then I think I won't. I won't show you. I'll be happy to answer questions, and I'll just show you the open problems for today. By the way, so step 2 is using the Penrose transform to rewrite the Euler-Lagrange equation in a way that we can analyze, and step 3 is to do the analysis. Okay, is why is that Euler-Lagrange not satisfied for any p? It's just based on sign considerations. We have a Euler-Lagrange that has the left-hand side and the right-hand side, and they have different signs. Okay, that's only accessible after you apply the Penrose transform to this Euler-Lagrange equation. Okay, all right. So open problems. We had a list from yesterday, we already talked about that for today. So this thing that I'm telling about the Penrose transform conformal map that sort of simplifies the analysis of the Euler-Lagrange equation on the cone. And the problem for the problem for Schrodinger is easier. So there should be a transform there, sort of conformal, pseudo-conformal map there that makes the analysis very, very easy. That hasn't been done. That's what I suggested as the first problem for open problem for today is applying not the Penrose transform, but something else called the lens transform, which is if you want the Schrodinger equivalent of the Penrose transform, to, for instance, reprove Chris kilogram and maybe see if you can extract something like you were asking for P different from 2. For P different from 2, we don't know anything except that maximizers exist. Maybe with a lens transform we could. All right, so this theorem is about the one cone. The one sheet cone. I told you that the 2 sheet cone is harder because we don't even have candidates, but it would be nice to do this critical point analysis. Okay, so do the same thing, talk the base theorem for the 2 cone. And of course, the really hard problems are the conjectures of Lie, that maximizers are always Gaussians, and the remaining cases are Fosk's conjecture. We know that Fosk's conjecture doesn't have a chance on the 2 cone in dimensions, but in all dimensions it does, and for the 1 cone it's possible. Okay. So that's I think it's a good idea.
Thank you. Your other questions or comments?
Just a curiosity, how did you come up with this Penrose transform? Did you expect it should be that one, or it's after you calculated it turns out to be Penrose transform?
I mean, there were some hints in the literature. So both the Penrose transform and the lens transform have been used to study wave and Schrodinger equation. The new observation that was part of Giuseppe's PhD thesis was to notice that the Penrose transform maps the candidate to being a maximizer to the constant functions. Okay, so that's the turning point.
Yeah, well, because it is the no binary is that function does not maximize the.
Not even does it not maximize, it's not even a critical point. It's not a critical point, it's not a local maximizer, it's not a global maximizer.
But by Ramal, they exist.
They exist, exactly. So what are they? Completely.
Other questions, Thank you, Diogo. See you. That's it.